or not? Okay. I hope you can. Yeah. Thanks. Okay, so yesterday I finished by describing some of the ideas of Robinson. There's a longer list in the notes. I think I will not take the time now to go through them. Let me just remind you that at the very end I mentioned this idea of completing theories rather than completing structures. And fortunately then Annan gave a detailed account of one of the important examples. The example he discussed wasn't elaborated till 1990 for reasons which I'll explain later. The earlier important example was differential fields and its completion. Now, curiously, both theories turned out later to have considerable significance for number-theoretic or Diophantine questions. But they were, well, actually the latter, ACFA, was looked at because of some intuitions about number theory, but it wasn't clear it was going to be related. Certainly differentially closed fields was not ever imagined to have any connection with Diophantine geometry when it was first formulated. Okay, so yesterday I discussed the early work from the 1930s onwards, and I spoke quite a bit about Tarski. I stressed Tarski's theorem for the real field and the fact that he gave an elimination theorem showing that projection was redundant if you started with a suitable stock of basic sets. I did not give any attention in my first lecture to the issue of axioms for the reals. Fortunately, Florian discussed it a little bit in his lecture. Let me just return to it briefly. So this is, to some extent, logically independent of the question of what the definitions are like. But it is important for a future analogy. So axioms for R. Now, there are actually two axiom sets, which don't look as if they've got too much to do with each other. So the first possibility is probably rather deeper algebraically. This is not quite what Tarski used, but it's close to it, and ultimately it relates to the work of Artin and Schreier on Hilbert's 17th problem and the invention of the notion of real closed field. Basically, the axioms for the field R, which would henceforward just be a general field K. So I'm going to look not only at R, but at fields elementarily equivalent to R. The axioms would be, in the language of field theory, that the absolute Galois group of K, so the Galois group of the algebraic closure of K, is equal to Z mod 2Z. And that's not quite the way Tarski gave his axioms. He said that the field has no extensions of odd dimension, so that's killing a large part of possible Galois group. And then his other axiom was in terms of order, that positive elements are squares. Now that in the end is equivalent to this, although this makes no mention of an ordering on the field. That's hidden in the Galois theory that Artin and Schreier had got hold of. But this is really the axiom for the reals. And it's a first order axiom. It may not be completely obvious that it is, but it's known to be a first order axiom. And the second set of axioms, so this is formulated without ever mentioning order. You can deduce from that if you define positive by being non-zero square, you have an ordered field, etc., etc. I mean, it's not very obvious that that's so for this. The other set of axioms are in the language of ordered fields. And they say the following. It's an infinite set of axioms. It basically is the sign change scheme. And it says that if a polynomial changes sign on an interval, it's got a root. Now, it's kind of fantastic that these are equivalent sets of axioms. I mean, the work of Artin Schreier on Hilbert's 17th problem is really very deep, and it links very nicely with modern model theory. So these are two sets of axioms, okay? Now, I want to concentrate on this one for the moment. It's, of course, an infinite set of axioms, one for each degree of polynomial. Okay. And then the axiom basically takes a generic polynomial of degree n and says something about it. So it's a statement about the coefficients of a polynomial of degree n. Okay. Now, something fundamentally important is the following observation. The original structure we want to deal with, what I was calling in my notes a core structure, something quite fundamental in mathematics, has tremendously tight structure. It's not merely an ordered field satisfying this property, it is complete. It's locally compact in the topology defined by the order. This is a consequence of that, okay? But most fields satisfying this, in fact, no other field satisfying this axiom is locally compact. R is the only one which is locally compact. This is sort of the first order trace of the completeness of R as an ordered field. Okay? And what is remarkable is that there's nothing follows from the completeness of R which can be formulated in the language of ordered fields which doesn't follow from this algebraic axiom. And it's well known that this has interesting consequences. One has these theorems about, classical theorems about division algebras over the reals, which are proved topologically, but they're actually true for any model of these axioms because they are first order statements, although one doesn't really know any elementary proofs of them. Okay. Now, the other thing I want to stress about the reals, we've alluded to it already, is that in some sense the topology is definable in the field language. When it's not entirely clear what one means by this, I really mean that uniformly a basis for the topology is definable by a formula, and it comes down to saying that x is bigger than 0 if and only if x is not equal to 0. And in the language which several people used yesterday, Francois, certainly Francois, x is not equal to 0 and x is a square. So this is an algebraic notion and this is an order theoretic notion, but they're equivalent in this situation. Okay, so today I'm going to talk about the p-adic fields, or the general p-adic field. And by that I'll understand not merely the QPs, but their finite extensions. Okay. And one important connection between the reals and those fields is that these are the only locally compact fields in characteristic 0. Oh, gee, I don't know what I'm doing. But of course, again, local compactness is not a first order property. There'll be fields equivalent to these things which are not locally compact. All right. Now, as I said yesterday, the issue of a metamathematical analysis of these fields had been raised, but probably rather late in the history of the subject. The first reference I saw was in this paper of Julia Robinson in 1963. The problem was solved in 1964. And I think the impression one has from Julia Robinson's paper is that the prevailing mood in the Tarski school was that this was not likely to be decidable, which seems a very misguided interpretation of things. Okay, so I want to stress that in the history of logic, say from Pressburger up to 1960, only one or two basic structures had been thoroughly analyzed and shown to be non-Gödelian. The reals, the complexes for which there's an elimination theory much more straightforward, and the algebraically closed fields of characteristic P, which I have not really discussed till now, and I'll discuss later. Okay? And Abraham Robinson did not really give a thorough analysis of any one of the classical structures by his methods, unless one counts the case of the valuation structure on algebraically closed fields. Okay. But there was a very trivial analysis given, so trivial that, for example, I certainly thought it was not important, but it turned out to be important later. Okay, and then suddenly the situation changed. Axon, Kochin, and Yershov those two working together, and Yershov working in Novosibirsk, independently solved the basic problem for those structures and for many other related structures. And I think it's clear that their main motivation was to find the p-adic substitute for this. To find an axiom like this which would control everything else. Okay? In terms of the considerations that Anand was using yesterday, these axioms are universal existential. They basically say, for all polynomials of dimension n, so that's of degree n, that's a statement about the coefficients. If something quantifier free happens, then something exists. So the universal existential axioms, the kind of things he was discussing yesterday, and it's known that those axioms constitute the model companion of the theory of ordered fields. So this is another example of completion, analogous to ACFA. Okay. Now, in fact, anybody who knew anything about the p-adics already knew the analog of the sign change property. So the analog of the second set of axioms its analog of second set is just Hensel's lemma. Which I'm not going to spell out. I think all the number theorists know it, and probably all the logicians know it. But basically, it says that if you have a polynomial over the valuation ring, let us say, you can do more generally, such that its reduction modulo the residue field has a non-singular 0, that can be lifted. So it's a criterion for providing a root of a one-variable polynomial. And it's a consequence, again, of the completeness of these p-adic fields. Okay? So this is a first-order axiom. And it's a consequence of completeness. On the other hand, it's rather easy to see that it will then have models which are not complete. Hence, various Henselizations and so on. So, all right. Now, let us just try to pursue for a bit the issue of the analogy, before I even state the X-Koch and Yershov results. Let's pursue the specific analogy between the reals and the p-adics. I mean, Hensel's lemma is true in the p-adics, but it's true in many, many other fields which occur in nature, power series fields, etc. Okay, so it's a rather ubiquitous thing. I want, for the moment, before I state the results, to look at some simple issues of definability. So analogies between R and QP. Now, of course, I mean, all number theorists know that they belong together. They're usually packaged together in the Adels or something like that. André We's book on basic number theory has a very flowery paragraph about the need not to, I mean, the obligation not to have any segregation here, etc., etc. Anyway, they do, despite the fact that the topologies are so very different, this one being connected and these totally disconnected, they have very strong algebraic and model theoretic analogies. And the most important one for what I want to say, in some sense, for some things that, say, Francois has been saying, is the following, that in QP, and in fact in all the finite extensions, the topology is also algebraically definable. Now, I managed to say this slightly wrong in my notes. There's a combination of a piece of dyslexia and a typo there. So let me just put the record straight. But the basic idea is this. We've got QP, and we've got the valuation from QP to Z union infinity. And this is an ordered abelian group, a model of Pressburger's axioms. This is a Pressburger thing. Okay, and then we have inside this, we have ZP. The x is such that Vx is greater than or equal to 0. And basically, once one knows ZP, one knows the topology. All right, so how can one define ZP inside QP without appealing to the valuation? I should also say that I'm proceeding a bit sloppily here. I've never really said, nor do I want to for the moment precisely, what language I'm dealing with here. You see, I've got the field, and then I've got this Z. So I'm really using a sorted language of the kind, again, that Francois referred to. But I want really to show that there's no need, in this case, to use a sorted language, that the sorting is irrelevant, that both Z and this ZP are somehow already interpretable algebraically inside QP. And the basic idea, well, I don't know to whom it's due, but Axe used it systematically in the early days. The basic idea is the following, that an element X is in ZP, this is for, first of all, for P not equal to 2, if and only if there exists a y squared equals 1 plus px squared. And this is the same as defining p-adically the relation that the p-adic norm is less than or equal to 1. Why is this true? If x has got negative value, this thing has got odd valuation. This has got 0 valuation, so this thing has got odd negative valuation. This has got even valuation, so it can't happen. On the other hand, if x has got value greater than or equal to 0, Hensel's lemma says that you can lift the trivial root 1 up to a root. Now, this doesn't quite work if p is equal to 2, and I said it wrong in the notes. I don't know what I was thinking about. For p equals 2, I managed to say for p not equal to 2 after that, you do something. I meant p equals, wait, what do I mean, for p equals 2, you have to use something slightly different. You could either use cubes, but that's slightly inelegant, or you can use something like this, exists a y equals 1 plus, I think, 4px squared is sufficient. Somehow or other, my dyslexia managed to convert this 4px squared into px to the power 8 in the notes. I still don't know how I did that, but anyway. This might not even be correct. Someone should check it. But there is a definition. Basically, the point is, in the two-adics, to check if something is a square, you have to check modulo 8 or something. Sorry? Yeah. Yeah, there must be a word for it. I don't know what it is. It's a very rare form of dyslexia or something. But yeah, anyway. OK, the point is, in any case, that there is in both cases, there's an algebraic definition of, say, the unit ball. Okay? And it's important to notice that in the reals, there is also a definition. Notice that if you take p equals somebody.
The second formula is characterizes the ZP for all.
Yes, yes, that's the point. I mean, I think I do say that correctly in the notes. I mean, dyslexia was suspended at that point. This is really the thing you should use generally. Alex typically said this works for p not equal to 2, and then you do something else. OK, now if you take p equals minus 1, and you look at the thing that says that there exists a y squared, which way is it? Y squared is 1 minus x squared in the reals. That defines the unit ball also. So maybe from this point of view, the reals are the minus 1 adics. Anyway. But the basic uniformity is that in each case, the topology is defined. Well, this has implications for the topology on the adels, that there's a uniform way of defining it algebraically. OK, now one other thing I want to say here. Now, of course, these are manifestations of these P2 predicates that Francois referred to yesterday. I'm saying that to be in the unit ball is to have 1 plus px squared being a P2. So I'm only using at the moment the P2s. Another thing I want to stress, this may seem a bit weird at the moment, is of course this depends on P. P is here, and P is here. And I mean, I would like you to think of this P becoming a T. Okay? You might imagine that you're working in the p-adics with an extra symbol for P, a uniformizing element or something like that. And then uniformly across the p-adics, you would have a definition of the unit ball. See, this is not uniform across the p-adics from the standpoint of logic, because this formula depends on P. It only becomes uniform if you replace P by one fixed symbol. Okay, now what, I won't state the X-Cochin results in full generality. They are tremendously general. But the basic shape of them is the following. They are, to begin with, they are axioms for certain Henselian fields. Complete sets for certain, but for many of the most important, now again, they are sensitive to the language one chooses. As I said, if you're going to deal with Henselian fields, Henselian value fields completely generally, it probably is best to work in a three-sorted structure. a field sort, a value group sort, and a residue field sort. One point of the maneuvers here is that I don't actually need the other sorts, because I can use this to define the relation value of x equals value of y. Value of x equals value of z, or something like that. So therefore, I can essentially interpret the value group. It's equivalence. This is an equivalence relation whose classes are the value group. And similarly, I can interpret the residue field. So in these particular classical cases, I don't need the other sorts. But in general cases, I might need them. Okay? So essentially, the axioms are the following. This is not the most general class of fields to which the X-quotient analysis applies, but I don't want to be too general here. First of all, that they are Henselian. Okay? I've stressed that that is a first-order axiom scheme, analogous to the sign change property. Secondly, that the value group is a Pressburger group. I've never actually given you the axioms for Pressburger, nor will I do so. I think it's a good exercise to figure out for yourself what are the axioms for Pressburger arithmetic.
Well, whatever the axioms are, I guess you mean anything that's elementarily equivalent.
Yeah, you want to find some axioms that give you anything elementarily equivalent to it. Basically, they are that you've got a discretely ordered group with the least positive element 1, and that you have Euclidean division for each standard integer, so that G modulo ng is canonically isomorphic to the remainders modulo n. And that is a complete set of axioms. Okay, so Henselian value group, Pressburger group. Now, a complete set of axioms for the residue field. Okay, so we take the point of view that the residue field is a simpler entity than the actual valued field itself. So much of the time, it should be easier to find axioms for the residue field. Now, it is dead easy to find axioms if the residue field is a field of 7 elements. You know, you just say there are 7 elements which add and multiply in a certain way. That's okay so far. Now, but it's not enough. You need some extra condition on the residue field. Either the residue field is characteristic 0, which is not the p-adic case, unfortunately, or the residue field is has some finite characteristic I want to stress this is not the most general set of axioms for which this works, but this is good enough for our immediate purposes. The residue field is of characteristic P, and V of P is equal to 1, the least positive element of the value group. And we would call that an unramified situation. That's what it would mean in a normal situation. So you call this unramified. Now, I have to cut a lot of corners, but basically, X and Cochin showed that if you're in this kind of situation, the complete set of axioms of the field is got by saying it's Henselian, the value group is Pressburger, and then giving a complete set of axioms for the residue field. Okay, so that provided a huge number of interesting complete sets of axioms for fields. In particular, it gives complete set of axioms for the p-adics. But it also gives complete set of axioms for various power series fields in characteristic 0. For example, it gave you axioms for formal power series over the complexes, because we know axioms for the residue field by Tarski. And it gave you axioms for the formal power series over the reals, because we know axioms by Tarski. So this already began to enlarge our stock of fields for which we understood the axioms. And sort of general technology shows that if you understand enough about the axioms, you will begin to understand something about the definable sets. You will understand what's going on in the, how the definition of something, say, in the field sort relate to definitions in the value sort or the residue sort, etc. Okay. Now, a fundamentally important class of fields to which this does not apply is the formal power series over finite fields. Because V of P is certainly not equal to 1, it's equal to infinity. And we don't know to this day a complete set of axioms for the formal power series over finite fields. Yeah. Now, it's routine to get out of this kind of thing decidability. There are general nonsense methods for getting decidability of the p-adics, etc. And they're not really interesting. They don't give you enough information. But at least they show that the p-adics are not sort of fundamentally Gödelian. You could not interpret the arithmetic of the integers in them, things like that. But it doesn't immediately tell you too much about the structure of definable sets in the p-adics. At any rate, this refuted Tarski's conjecture that the only decidable fields were the reals and the algebraically closed ones. I mean, there are lots of others. Of course, there's only countably many such theories, just by counting arguments, but there are many. And you can iterate these power series things. You can't work with power series in two variables, but you can take, anytime you have a decidable field in characteristic 0, you can take power series over that and get another decidable field.
Power series in two variables open then?
No, it's they're undecidable, I think almost always. I think always probably, yeah. I mean, there are some important things known about them model theoretically, but the full theory is essentially chaotic. Okay, so this, as I said, tells you about the axioms. So this provides the analog of Tarski's second set of axioms. Now let me just make a digression. This was a rather late discovery, and I find it a really tremendously beautiful discovery. It's not really originally a logical discovery, but it fits this picture very well. So what about axioms for QP of the first kind, Galois theoretic axioms? And miraculous thing is that there are Galois theoretic axioms for QP that don't refer at all to Hensel's lemma or anything else. Just as in the reals, there is this axiom that Artin and Schreier found, which doesn't refer to the order, but tells you everything about the order. Now this, a number of people contributed to this. The basic insights, I think, come from Neukirch, and the, the ultimate work was done by Koenigsmann and Popp. Let me just tell you something about the Galois group of QP. So, Gal QP, of course, is a profinite group. It's known, and it's only fairly recently that it's been known completely. I think the first systematic study of it was made by Iwasawa around the early 1950s. But he did not give a complete analysis of the group. Essentially, this group is 3 or 4 generated. Let's say it's generated by topologically by 4 elements. Of course, it's an uncountable group. And there is a presentation for it, which involves principally so-called tame relations relating to ramification. The essentially important relation in it is something like a Higman-Neumann-Neumann relation from combinatorial group theory. It's essentially something like this, sigma inverse tau. Sigma is tau to the p. So the presentation depends on p in the exponent. But there's slightly more to be said than that. I mean, the wild ramification is the fundamental problem in all of this. At any rate, it is a theorem in logic. Well, perhaps it was never explicit until an unpublished paper about 20 years ago by Van der Vries, myself, and Cherlin, but it's somehow folklore, that to say of a field that its Galois group is a specific finitely generated profinite group is an elementary condition. It's given by a first order set of axioms. So the condition on K that gal K is isomorphic to gal QP is first order. This is not really completely obvious. And what was proved from Neukirch's work, then by Koenigsmann and Popp, is that any field whose Galois group is isomorphic to QP is elementarily equivalent to QP. And I find this a fantastically beautiful result.
What's the idea of this first order?
Of this, how to say it? Okay, basically, you will describe a finitely generated profinite group by saying what are its finite quotients of every size. And there's only finitely many of each size. And these will correspond, of course, to field extensions. So suppose there are 10 extensions of dimension 11. You can say that by saying something about matrices and so on. It's ugly, but nevertheless, it's a first order set of axioms. And what is amazing is that simply out of this group theory condition, Hensel's lemma follows. Maybe not quite so surprising that P comes out because it's in one of the relations. Even that's not obvious. But that Hensel's lemma comes out of this is really rather startling. And so far, I don't think this has been used for any purpose. I suggest in the notes a possible use for it. Maybe somebody might take this up. I won't pursue that now. Okay, so now Francois yesterday referred to this quantifier elimination that I discovered. This work was done in 1964, and it came to my attention when my supervisor at Stanford produced a paper from his desk and said, I'm never going to read this, and sort of threw it at me. And it was the preprint of Axiom Coaching, which essentially changed my mathematical career completely. So I worked on these things a bit, not in my thesis, but subsequently, and I eventually, by thinking constantly about the analogy between the reals and the p-adics, I found this elimination. You see, so as Lazare said yesterday, there is an elimination in QP using the power predicates.
I'm sorry, just back you up again.
Mm-hmm.
I may be simply asking.
Oh, I'm supposed to repeat your question. Sorry, I forgot. Yeah.
I may be simply asking the question again, but is the converse true?
I mean,
K elementary equivalent.
yes. It is true also. You can say, I mean, for a finitely generated topological group, you can say of a field that its group is that. This is not perhaps ever explicitly spelled out in the literature. It is in this paper of ours. It was a 3-author paper, which was, I think, is a good paper, submitted to Krella. A very tiny inaccuracy we discovered in the middle of it. Not difficult. We knew 3 different ways to correct it, and we couldn't decide on who should write it and which method should be used to correct it. So the paper was never published, but it's in there. Okay. No, it goes backwards as well.
But should this be, do you expect this to be true for any field?
No, I mean, in fact, Königsmann showed, didn't he, that the only fields for which you can really characterize the theory by the Galois group are very restricted. They are just basically p-adic fields and the reals, isn't it? And maybe a little bit more. It's very tight. I mean, this kind of alternative axiomatization is very rare.
The finite fields will give complex numbers.
Pardon?
Yeah, Z hat and it's not elementary.
Yeah, the finite fields of z hat, and then there's lots of other fields of z hat. We'll see plenty of them later in these lectures. But the condition on a field that it has z hat as its group is first order, because it's just saying there's a unique extension of each dimension. That's maybe the easiest way to see a special case of this result. So, I mean, Florian was asking me why I thought of these PNs. There were various funny bits of motivation. I also thought of them in a panic. I was going to give a talk at Princeton once, just after I went to work at Yale, and I was a bit afraid of giving a lecture in front of Cochin, and I thought I'd better kind of soup up what I knew about these things. I thought very hard on the train, and I found this quantifier elimination, basically. But there were a number of ideas in it, and I think some of them are quite interesting. First of all, one explicit motivation I had was that this group is not only like this, it's actually a pro-solvable group. All the normal extensions of the p-adics are solvable. Again, you can find this kind of scattered here and there in the literature. It's probably folklore a lot of the time, but it's explicit in Serre's book on local fields and various other places. So I thought, well, there was a general feeling that, I mean, using various more abstract ideas in model theory, you could only understand the theory of a field if you understood simultaneously the theory of all its extensions. If they were all solvable, nth roots were somehow a crucial thing. So why not use these predicates? I mean, that would not be enough to do it, but that was a motivation. Well, there were various others. It was also, the PNs were somehow a means of coding inside the field Pressburger. Basically, something can only be an nth power. It's not an if and only if, but something can be an nth power only if its valuation is divisible by n. And in Pressburger, the predicates n divides something are fundamental. So that was also involved in it. But there's another point of view I think is important. It's certainly important for the more advanced developments that others did later. I mentioned yesterday, this is again the analogy with the reals. Of course, I've stressed the fact that in the reals, the order is defined by P2. Okay? Well, another point I should make is that in the p-adics, the multiplicative group of the p-adics modulo the nth powers is finite. And there are really two components to that. One is that in the residue field, the corresponding thing is true, and then in the value group, the group modulo n times itself is finite. That's really the reason that this is finite. Okay, now in the case of the reals, for n equals 2, this number is 2, and it corresponds to a plus or minus. Corresponds to the order, eventually. Now, I mentioned yesterday that in the case of the reals, Tarski had in principle a means of proving very extraordinary results in the 30s about the structure of real semi-algebraic sets. He could have, by his methods, shown that sets in arbitrary dimension have finitely many connected components, the sum of the Betti numbers is finite, finitely many homeomorphism types within families. Many, many things could have been done by bare hands once he knew his elimination theory. And it took many years until logicians understood that, thanks to the efforts of Van den Dries, and Pillai, Knight, and Steinhorn, and so on. And that's now a huge theme in model theory. But Tarski could have done that in the specific case of the reals in the 30s.
I'm sorry, I just didn't.
Well, let me see, definable sets. Okay, I mean, a definable set in n-dimensional space, if I was doing it in arithmetic, it's an unintelligible thing. If I'm doing it in the reals, it turns out that definable sets are finite unions of cells. Basically, they can be stratified by manifolds. And a typical cell is something like this. The bit in between, this is a definable function. A definable function is a function whose graph is a definable relation. So I have two definable functions on a certain interval. One is below the other. So this intervening thing is a definable cell. And clearly its topology is pretty simple. Also its geometry and so on are simple too. Tarski would have been able to show, one can show by his methods, that in the semi-algebraic situation, every set is a union of cells of this kind. Now, the crucial thing is being on one side or other, say, of a hypersurface or something like that. So the two cosets of the squares are somehow relevant. I might say of a polynomial that it's suppose I say that f of x is not equal to 0 and P2 of f of x, okay? That's putting me on one side of a hypersurface. And if I put instead P2 of minus f of x, I would go on the other side of it, okay? Now, my motivation in the p-adics was that there was something similar going on. I mean, the two cosets here provide you a sort of orientation. In the p-adics, there are continuum many orientations corresponding to the different cosets for the nth powers as n varies. So in some sense, you could be on, if you have a hypersurface, you can be on finitely many sides of it. So, but that gives you a notion of cell. See, there's no a priori obvious notion of a p-adic cell. And the existence of a cell decomposition in the p-adics was obtained by Denef, first of all, and it was fundamentally important for the kind of work that Lazare is describing. I don't want to pursue this further because it will certainly come up again in Lazare's lecture. But this was an important aspect of the PNs, that they were a natural thing for providing a notion of cell decomposition in the p-adics. Moreover, there are other aspects to this I don't have time to enter into. Van den Dries and Scowcroft showed that there's a notion of, in both the reals and the p-adics, or in all models of them, there is a notion of dimension of a definable set, which you can define model theoretically. You define it, first of all, model theoretically, and then you show that the dimension of a definable set is actually the algebraic geometric dimension of its Zariski closure, which is a good result. That depends on knowing something about the nature of definable functions. Definable functions in both the reals and the p-adics are locally algebraic. So there's a lot of results analogous between the reals and the p-adics that follow from this kind of thing. Okay. Now, I have not much time left. What I want to discuss very briefly is the issue of uniformity now in P. This will be a dominant thing in what follows. What kind of uniformity do we have? By that, I mean, I've given an elimination theorem for the p-adics, quite a useful one. How uniform is it? Basically, within a given p-adic field, I'm showing that a certain kind of set is equivalent to a Boolean combination of p-adic cells, or something like that. Okay? The issue is there a uniformity in P for this? Now, this takes us into pretty deep water, because my elimination used tacitly the fact not only are these dimensions finite, these quotient groups finite, but the coset representatives are given by ordinary integers. That's very easy to see. But what the integers are for a given n, of course, depends on P. So there's a certain lack of uniformity in the elimination. So one can ask, is there an elimination theorem analogous to the one I'm giving, but which is uniform in P? Now, this has been looked at for a long time. It's really only now that one has a truly satisfactory analysis in this motivic approach that Lazare is about to begin describing. But that came late. People looked at this rather earlier. So let me just give you one idea for today, and I'll return to it tomorrow. Suppose I've got different p-adic fields. Okay. Each one has got its residue field. And if I take a sort of distinguished symbol for a uniformizing element here, just for convenience. Now, as P gets bigger, the residue fields get bigger. Okay. The value group in all cases is Z. And V of the uniformizing element is 1. What happens when P goes to infinity? What is the meaning of this model theoretically? Well, I had hoped I would say more on this today, but it'll have to be at the beginning tomorrow. And I'll try to do it in a more geometric way than model theories usually do it. The point is to understand uniformity of definitions in the family of QPs, you have to go to some kind of limit. In fact, not just one kind of limit. You've got to go to many different limits. Out here, there are certain entities, limits, as P goes to infinity. There are certain valued fields, Henselian valued fields, the value group is equivalent to Z. But the residue field is this thing which is certainly far out the first time one sees it. It's an infinite finite field. I mean, this is a bit sort of sloganistic at the moment. I'll make it rather more explicit tomorrow. Sort of in the language of the trade, what you really have to consider here is an ultra product of finite fields. And in fact, it can be made rather concrete. Let me just say what it really is to an algebraist. For example, Serre uses this description in the motives book. The things that are out here are really of the following form. You take a product, you take the product of the FP, so that's not a particularly nice ring, and you divide out by a maximal ideal, a non-principal maximal ideal. This is not the way that logicians first thought of these things, but Cochin certainly knew this point of view around 1970 or so, I suppose. And the question is, what kind of thing is this? It turns out that to understand the uniformity of definitions here, because you can code the residue field, you must be able to understand definitions here. And in particular, you must be able to understand axioms here. What is this thing? What kind of field is it? Now, one thing, fortunately, in view of the questions, one thing I can say is that the Galois group of this field is Z hat. You could do that by bare hands from this definition I've given here. So the Galois group is nice. What is truly beautiful is what Axe discovered using the Riemann hypothesis for curves, is that this thing is almost algebraically closed. It's not algebraically closed because its Galois group is Z hat. On the other hand, it's really not algebraically closed only because of one variable phenomena. Absolutely irreducible varieties over this field have points in the field. Now that is true because of the Riemann hypothesis for curves. It's not true in any of the finite fields, but it's true once you kind of smear them out in the limit. And then it turns out that these fields have an elimination theorem a little bit like what I was discussing here, but instead of considering the nth powers only, you have to consider, well, related predicates, which I'll explain tomorrow. And Axe was the person who took this step to consider these entities. I'll say a bit more about them tomorrow. And this was, I would say, in many ways more revolutionary than this. These things had never been seen before, basically. And they do occur, or things elementarily equivalent to them do occur in nature, in some sense. So I'll describe them. I mean, unfortunately, the construction belongs to what Mumford calls, well, Mumford has a description of this construction in his Red Book of Schemes, where he refers to it as, I forget now, some far-out construction of the logicians. But in fact, this far-out construction is involved in the kind of things Anand is talking about and so on. So I'll discuss this tomorrow. Thanks.
Okay, thanks. Are there any questions? If not, we'll meet again. 5 minutes break is okay? 5 minutes? Yeah. And thanks to Angus again.